This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to today's discussion. We'll be delving into a research paper focusing on a novel control framework for robotic manipulators in space, specifically for in-space servicing. The paper proposes a hybrid genetic fuzzy LQR controller. What are the key challenges in designing controllers for such applications, and how does this approach aim to address them?
The primary challenges in designing controllers for in-space robotic manipulation stem from the need for high reliability, robustness to uncertainties, like temperature fluctuations, sensor noise, and variations in the satellite's mass properties, and the ability to handle nonlinear dynamics. Traditional methods like pure LQR, while optimal for linear systems, often fall short in these complex, nonlinear space environments. This paper attempts to overcome these limitations by combining the explainability and adaptability of genetic fuzzy systems, GFS, with the optimality guarantees of LQR.
The paper mentions the increasing number of satellites in orbit and the associated need for autonomous servicing. How does this context influence the design choices and performance requirements of the controller?
The sheer number of satellites necessitates autonomous solutions. Human intervention is impractical and risky. Therefore, the controller must be highly reliable and robust, minimizing the risk of failure during critical operations. Performance is also crucial. Efficient and timely completion of tasks is essential for maximizing the operational lifespan of satellites and minimizing downtime. The proposed hybrid approach aims to deliver both reliability and efficiency.
The paper uses a 2 degree of freedom, 2DOF, planar robotic manipulator as a testbed. Why this simplification, and what are the limitations of this approach in relation to real-world scenarios?
The 2DOF planar manipulator served as a simplified model to validate the core concepts and algorithms. It allows for a more manageable computational complexity during the development and testing phases. Extending this approach to more complex, multi-DOF manipulators with more realistic dynamics is a natural next step. But the 2DOF model provides a crucial foundation for demonstrating the effectiveness of the proposed control strategy. The limitations include the lack of consideration for factors like joint flexibility, actuator dynamics, and the three-dimensional nature of real-world space operations.
Let's discuss the core of the controller, the hybrid genetic fuzzy LQR. Can you elaborate on the roles of the genetic fuzzy trees, GFT, and the LQR components?
The GFT acts as an adaptive gain scheduler for the LQR controller. The LQR provides the optimal control law for a linearized system, but the GFT learns to adjust the weighting matrices, QNR, of the LQR based on the current state of the manipulator. This allows the controller to adapt to nonlinear behavior and uncertainties. The genetic algorithm optimizes the fuzzy rules within the GFT, effectively tuning the controller's response to different operating conditions.
The paper highlights the use of Theory's True AI Toolkit. What specific functionalities of this toolkit were leveraged in the development and optimization of the controller?
The True AI Toolkit provided a streamlined environment for implementing and optimizing the GFT. It offered pre-built functions for creating and training fuzzy inference systems, implementing genetic algorithms, and integrating them with the LQR controller. This significantly reduced the development time and effort, allowing the researchers to focus on the core control algorithm rather than low-level implementation details. The toolkit's built-in GA also simplified the optimization process by automatically determining optimal hyperparameters.
The results show that the genetic fuzzy LQR outperforms optimal LQR in terms of a defined cost function, which considers settling time and control effort. Can you elaborate on the specific improvements observed and the trade-offs involved?
The genetic fuzzy LQR achieved an average performance improvement of approximately 18.5% compared to optimal LQR across various scenarios. This improvement is primarily attributed to the GFT's ability to adapt the LQR gains to the nonlinear dynamics of the manipulator. However, in some cases, the genetic fuzzy LQR exhibited slightly higher control effort. This suggests a potential trade-off between settling time and control effort, which could be further optimized by adjusting the cost function or the GFT architecture.
The paper also conducts a robustness analysis. What types of uncertainties were considered, and how did the genetic fuzzy LQR perform compared to the optimal LQR under these conditions?
The robustness analysis involved introducing uncertainties in the manipulator's mass and length parameters, varying them randomly within a plus 10% range. The genetic fuzzy LQR demonstrated significantly improved robustness, achieving a 100% success rate in reaching the target state, while the optimal LQR succeeded in only 89.8% of the cases. This highlights the adaptive nature of the GFT in compensating for parameter variations.
The robustness analysis also revealed higher control effort for the genetic fuzzy LQR under uncertainty. How can this trade-off be addressed in future work?
The increased control effort under uncertainty is a trade-off that can be addressed by refining the cost function to place more emphasis on minimizing control effort while still maintaining acceptable settling times. Alternatively, the GFT architecture could be modified to better balance the trade-off between performance and control effort. Further investigation into different membership functions and rule bases within the GFT could also lead to improvements.
The paper concludes by suggesting avenues for future research. What are some of the key directions you see for extending this work?
Several promising avenues exist. First, exploring different cost functions to better balance performance and control effort is crucial. Second, extending the approach to higher degree of freedom manipulators and more realistic 3D models is essential for real-world applicability. Third, incorporating more sophisticated uncertainty models and robustness analysis techniques would enhance the controller's reliability. Finally, rigorous verification and validation methods are needed to ensure the trustworthiness of the controller before deployment in critical space applications.
The paper mentions the use of Takagi-Sugeno-Kang defuzzification. Could you elaborate on the choice of this method and its implications for the controller's performance?
The Takagi-Sugeno-Kang TSK model offers a good balance between computational efficiency and accuracy. Unlike Mamdani-type fuzzy systems, which use linguistic outputs, TSK systems use linear functions as outputs. This makes them easier to integrate with the LQR controller, which operates on numerical values. The choice of TSK also contributes to the overall explainability of the system, as the linear output functions can be readily interpreted.
The paper emphasizes the importance of trustworthiness in space robotics. How does the explainability of the genetic fuzzy system contribute to this aspect?
The inherent explainability of fuzzy systems is a significant advantage in safety-critical applications like space robotics. Unlike black box methods like deep reinforcement learning, the fuzzy rules and membership functions in the GFT provide insights into the controller's decision-making process. This allows engineers to understand why the controller is making specific control decisions, increasing confidence in its behavior, and facilitating debugging and verification.
The paper uses Runge-Kutta fourth-order integration. What are the considerations in choosing a numerical integration method for this application, and why was Runge-Kutta 4 selected?
The choice of numerical integration method is crucial for accuracy and stability. Runge-Kutta fourth order is a widely used method that offers a good balance between accuracy and computational cost. Its higher order of accuracy compared to simpler methods like Euler integration reduces the accumulation of numerical errors over time, which is important for long simulations. The selection likely reflects a trade-off between accuracy requirements and computational resources available during simulation.
The paper mentions a maximum allowable propagation time of 10 seconds and a tolerance for ending propagation. What are the implications of these parameters on the controller's performance and the overall simulation?
The 10-second limit prevents simulations from running indefinitely if the controller fails to converge. It acts as a safety mechanism to avoid excessively long computation times. The tolerance parameter defines the acceptable level of error in the state variables before the simulation is considered to have reached the target state. A smaller tolerance would lead to more accurate results but could also increase computation time. The choice of these parameters reflects a balance between accuracy, computational efficiency, and the practical constraints of the simulation environment.
The paper uses a fitness function that combines settling time and integral absolute control (IAC). How does this choice reflect the design priorities and trade-offs in the controller design?
The fitness function directly reflects the design priorities of minimizing both settling time and control effort. Settling time is crucial for efficient task completion, while minimizing control effort reduces energy consumption and wear and tear on the actuators. The combination of these two metrics in the fitness function represents a trade-off between speed and efficiency. The weighting of these two terms in the cost function could be adjusted to prioritize one over the other, depending on the specific application requirements.
The paper mentions that the R gains in the LQR controller were kept constant. What was the rationale behind this decision, and what are the potential implications?
Keeping the R gains constant simplifies the optimization problem by reducing the dimensionality of the search space. This allows the genetic algorithm to focus on optimizing the Q gains, which are more directly related to the manipulator's state and the desired performance characteristics. The potential implication is that the controller might not be able to achieve optimal performance in all scenarios, as the fixed R gains might not be ideal for all operating conditions. However, this simplification is a reasonable trade-off given the complexity of the overall optimization problem.
The paper describes the training setup, including the number of scenarios and initial conditions. How was this training data selected, and what are the implications of the choice of training data on the controller's generalization capabilities?
The training data was carefully selected to cover a range of initial conditions and target states. The choice of 88 scenarios, with variations in initial joint angles and target positions, aims to provide sufficient coverage of the manipulator's operational space. The selection of initial conditions with A1 equals 0 degree and A1 equals 180 degree helps to assess the controller's performance across different configurations. The generalization capabilities of the controller depend heavily on the representativeness of the training data. A more extensive training dataset, covering a wider range of conditions, would likely improve the controller's ability to generalize to unseen scenarios.
The paper shows the training history of the genetic fuzzy LQR controller, what insights to be gained from this training history, and what are the implications for the controller's convergence and stability.
The training history provides valuable insights into the convergence behavior of the genetic algorithm. The steady decrease in the cost function indicates that the algorithm effectively optimized the controller's parameters. The final cost value of 0.815 suggests that the genetic fuzzy LQR achieved a significant improvement over the optimal LQR. The shape of the curve can also provide insights into the algorithm's efficiency and the potential for further optimization. A smoother, more monotonic decrease would suggest a more efficient optimization process.
The paper presents the FIS control services, what information can be extracted from these services, and how do they relate to the controller's decision-making process.
The FIS control surfaces visualize the mapping between the input variables, error and error rate, and the output Q gains. These surfaces reveal how the controller adjusts the LQR gains based on the current state of the manipulator. The shapes of the surfaces reflect the controller's decision-making logic. For example, steeper slopes indicate a more aggressive response to changes in the input variables. Analyzing these surfaces can provide insights into the controller's behavior and identify potential areas for improvement.
The paper compares the performance of the genetic fuzzy LQR and optimal LQR on a single case. What are the key observations from this comparison, and how do you support the claims made in the paper?
The single case comparison visually demonstrates the differences in control behavior between the two controllers. The genetic fuzzy LQR exhibits a quicker settling time, but potentially at the cost of higher control effort. This observation supports the paper's claim that the genetic fuzzy LQR can achieve faster convergence, but might involve a trade-off with control effort. The comparison highlights the adaptive nature of the genetic fuzzy LQR, which allows it to respond more effectively to the nonlinear dynamics of the system.
This has been a thorough discussion of the paper's key findings and implications. Thank you.